Here we go. Notes for 8.2. This is all about applying our proportions that we worked with in 8.1, and we're applying them to geometry. And the idea is this. If we want to create an idea of not congruent, but similar, so instead of using this symbol a lot, we're going to be using just this symbol. We have to use proportions to help us make that possible. Number one, how do we define a similar polygon? Well, you have to have a similar shape, which means that the angles need to be congruent. But the sides don't have to be. They just have to be what we say proportional. Now, for sides to be proportional, that means that there is a constant ratio between them. And working with that ratio, finding what it is, will be kind of the trick, so to speak. All right, here's our first example. The book is a little unclear when it shows you two figures. Are we going from the bigger one to the smaller one? Or are we going from the smaller one to the bigger one? Are we, in other words, making it larger, or are we reducing it? Now, if we were to look at it as using a ratio set equal to another ratio, i.e. a proportion, if I say x is to y, then we would say 12 is to 7. And likewise, if I said y is to x is equal to what ratio, then we would say 7 is to 12. Now, only one of these two is the correct ratio for this problem. And by the way, the book is unclear, and so I'm going to say our general practice is going to be left to right, if it doesn't say. So we're going to assume we're going in this direction, from the bigger one to the smaller one. Hopefully you see which of these two is the correct one. Why? How would you know that? Because we're always going to compare to 1. If your ratio is bigger than 1, like this one, then we're doing an enlargement. We're making it bigger. Whereas 7 to 12 is a number smaller than 1, and it's a reduction. And that's exactly what was going on in this problem here. We are reducing because we're making it smaller. All right? Fancy word for making it larger, dilation. All right, an example for a dilation might be something like this, 12 billion to 1. This would be, for example, Earth, and this might be a globe in your hands that you're holding on to and looking at, or spinning, might be in your room. There's one in my classroom here, okay? If we make it smaller, we call it a reduction. So here I've taken the letter R, and it's a little bit unclear what these numbers are. Black. All right, let's go 24 and 16. And so if I reduce this R, then we would say, okay, well, we're going to take 16 over 24 because that's the ratio that's less than 1, and we reduce it down to 2/3. So there is my reduction ratio, okay? If I have to prove shapes are similar, the two things that you're going to have to work with is show that the sides are proportional and that the angles are congruent. All right, in this problem here, I don't have to prove that the shapes are similar because it, notice, says here in this statement that ABC is similar to DEF, okay? And that symbol there is the similar symbol. So what we need to do is now just set up the ratio. So again, I'm going from here to here. This should be an enlargement, all right? So we should say 4 will actually go on the bottom, and 8 will go on the top. Now, how did I know 8 and 4 were corresponding? A lot of people are going to say that's on the left side, that's on the left side. That's how we know. No, it's because AB is first and second, and DE is second and third. All right? Likewise, for example, is that equal to 12 over 6? And is it equal to 10 over 5? And all of these are equal to the same ratio of 2 is to 1. So the answer is yes, these are similar. All right? 8.2, perimeter ratio. Find the lengths of each side of MCN. And we see that there is a dilation. MCN is the larger one, MED is the smaller, and the ratio is 2 to 1. So find the lengths of the corresponding sides. So here we see this side here is 3, this side here is 6. This side here is 4. This side here is 8. And we need to then find the diagonals. How do I find these sides here? All right? So, labeling those sides down, we say MD is equal to 3. NM is equal to 6. ME is equal to 4. MC is 8. And then we're going to finish up with ED and CN. Now we only need one of these because then we know the ratio already. So let's go with the small one. Hopefully you remember your Pythagorean theorem here. We've got one side equal to 3, another side equal to 4. And if you square both of those and add them up, and then take the square root of that, bam, you get 5, aka 5. So ED is 5, and CN is therefore 10. All right? This is an interesting question to talk about the area ratio. How many little triangles are in the big triangle? So if our ratio is 2 to 1, some people think that for every 2 small triangles, so 2 small triangles will equal 1 big triangle. Now in this case, you're actually going to end up with 4. Why is it 4, you might ask, you might wonder, okay? Well, let me draw the triangles. So do you see now that the big triangle has 4 of the little triangles? So why did the area ratio double on us? Why did it go from 2, even though we increased the sides by doubling, the area went to 2? So here we have the side, and here we have the area. That's because we have a one-dimensional shape, and this is a two-dimensional shape. So when you double or triple, you will square whatever number this is. So 2 squared is 4. All right? Little side note there to keep in mind. Find FG, GH, and EH. Now again, to find these, make sure you always know the corresponding parts. Look on your diagram. So AB corresponds to EF. Yes? That's going to be our main setup. So we could say 9 is to 6. Now notice I can change 9 is to 6 and reduce that down to 3 is to 2. All right, so then we take FG is to 4. So I've set that up over here. And solving that problem, I think we get 12 is equal to 2FG. So FG would then equal to 6. And then likewise, we would take 3 is to 2. And we'll do one more here. So EH is to 7. Make sure you set up those ratios appropriately there. That is, you put the EH in the right spot because it's the larger side, so it goes with the 3. All right? Again, 21 is equal to twice EH. So EH would be 21 over 2, aka 10.5. And perimeters between similar figures are proportional to the sides because this is a one-dimensional shape. But areas are also proportional to the square of the sides because this is a two-dimensional shape. All right, last problem here. I guess we got 2 more problems here. Given that triangle blah is similar to POM, angle H is 90, so now I know angle O. Oh, they asked me for measure of angle O here. It will be 92. But it's equal to 1/2 y, according to right here, right? So, therefore, y is equal to 180. Well, x is measure of angle M, and M corresponds to K. Yeah, and let's see, they don't give us K. Oh, but they give us H and J, right? So 180 minus 130 will equal K. So measure of angle M is 50, which is x plus 5. So subtracting 5 from both sides, we get x to be 45. All right. Now, yes, finally, setting up the means and the extremes on this problem is kind of important. Bat and dot, so keep those straight to each other. And so we know OT is 15, and OT corresponds to AT. So 15 is 2. AT is x plus 15. Now, sadly, this is a ratio, but I don't know what it's equal to, right? So I'm looking now at the diagram and I'm saying, okay, what sides do they give me that correspond that are both numeric? And I see down here, BT and TD. Again, check up here, BT, DT. Yes, that shakes out. So I can say OT and AT is the larger. So this is small, this is large, right? OT, AT. So make sure that you get the same thing over here, and the 9 goes upstairs, the 12 goes downstairs. Okay? Again, we're going to do the extremes and means. So extremes and means. So 15 times 12 has to equal 9 times x plus 15. 15 times 12, I think, is 180, maybe. I hope I did that right. And we get 9x plus 135. And so I subtract 135 from both sides, and I get 45. And so I get x to be 5. So find the value of x. X is 5. How long is AO? AO is also 5. All right, hopefully that worked out and you understood it and can do the problems. Best of luck. Go Argentina.